Welcome back to the information retrieval course. And with this, we start the actual content part. The first set of content videos will be refreshing some of the techniques that we usually teach to bachelors. Again, we call this course IR0. And here we will recap some of those things. So first, I'd like to quickly discuss the pipeline that we usually use in information retrieval to build such system. First, we need to acquire data. There are many ways to acquire data, but if we talk, for example, about web search, that will be through crawling mainly. After we acquire data in some way, for example, using crawling, we need to analyze the text, and that we will talk about later. We need to extract links and analyze links, again, if we talk about web search, because links mainly present in web search and just a few other domains, but in many domains, there are no hyperlinks. And finally, you use both text and links to index the information that you downloaded or crawled. And by this time, you already have the data prepared for searching. So this is the whole pipeline that we usually teach in, let's say, IR0 course. But for this course, for IR1, we will only need text analysis and indexing, and that's what we will talk about in the next two sets of videos. So we will start with text analysis. Text analysis will be discussed in 4 different aspects. First, we will talk in general about statistics of written text. Then we will discuss the general text analysis pipeline, talk a little bit about stemming and a little bit about phrases. And that's all you will need to know at this point. So let's start with the statistical properties of written text. And there are two important laws that you really need to know. The most important one is Zipf's law. Many of you have seen it. It's actually just a power law, but applied to written text. And what it says is the following. Basically, if you take all the words in a language, it doesn't matter which language, it's English or any other language, take all the words, count the frequencies, which means the number of times they occur in the language, and you rank them by their frequencies or by their normalized frequencies, which here called probability of occurrence, then you will see power law. These are the most occurring words here, the top 10 most occurring, for example, and these are the least occurring terms, and these are the probability of occurrences, and you will see the power law. So basically, you will see that the frequency of a word is inversely proportional to the rank of this word in this ranking. So the higher the frequency, the lower the rank, right? And for example, for English, if we take the probability, this probability and this rank, then this constant is 0.1, for example. For different languages, it's different. But importantly, this law holds for all the languages and even for all the n-grams. We'll mention that later. So if you take all the possible bigrams, trigrams, and any n-grams and put them all together, they still follow the Zipf's law. Now, some examples. Here we have top frequent words in English. So these are the words. So basically the most frequent word according to this particular study is the, and of, and so on. And this is the 50th most probable word, which is people. The second column is frequency. Third column is certainly rank. Then the probability, which is a normalized frequency. And then this quantity rank multiplied by the probability. And actually this quantity, the law says that this quantity should be constant. And if you look somewhere in the middle of this ranking, and indeed it's pretty constant, it is pretty close to 0.1, the constant that I mentioned here. So I mentioned 0.1, and indeed you see that it's 0.09 actually, 0.093, something like that. But in the beginning, there is certain deviation from that law, only for the top, I don't know, 10, 15 words. But then it stabilizes and it's, you see, pretty stable at 0.09. If we have a look at the very different frequencies. So this is a very frequent word. This is very infrequent word that appears once. So you see that actually, again, for very infrequent words, this multiplication of rank by probability deviates somewhat from the law, but normal frequency, 5,000 is not a lot. Actually, it's still around 0.1. So if we plot it on log-log scale, this is the rank, this is the probability. So the main body of terms is indeed along this line. So the rank is inversely proportional to the probability. But on top, these are very frequent terms, a little bit of deviation, and for very infrequent terms, there's a lot of deviation. This is the actual collection. This is an actual collection of words. But in general, so this is the most terms. So these are very, again, very infrequent terms. Those words are very few. Well, they occur very few times, and these are the most occurring words, and they follow this law. This is important to know. So that, of course, affects the analysis. The compression, and so on and so forth. Second law, it's actually probably affects the text compression techniques even more. It's called the Heaps law, much less known than Zipf's law. And the Heaps law actually says that the number of unique words in a language or in a collection is sublinear. So these are unique words in our vocabulary, and these are all the words in our collection or language. And you see that the dependency is not linear. So the number of unique words doesn't grow linearly with the number of words we use in a language. So the more words we use to write a text, for example, the more we tend to repeat the same words over and over again. It doesn't mean that if our text is long, then it will have very, very many unique words somewhere up there. No, if our text is long, it will have not much more unique words, not many more unique words than a short text, for example. Here, it's the law is actually the vocabulary size, the number of unique words equals constant by the number of all the words to the power of a certain constant. And again, for English, well, okay, these are the general, I don't remember what is the K for English, but here you can see that K is 62.95 for this particular collection, and beta is 0.455. So beta is usually around 0.5, and K varies quite a lot. K is this constant here. So these two laws, you just need to know them, that a text follows these laws, and that may be important in very many different applications.